So let's start. So this is week 3 of our reinforcement learning course, and today we start to work on more realistic problems, namely environments in which we do not have access to exact mechanics how this environment evolves. So last week we covered value-based methods, which allowed us to find an optimal solution for the environment in which we knew the exact transition model and in which we could iterate over all possible states. And to do that, we needed the state space to be discrete, finite, and not too big, so that we can iterate over all states in a reasonable amount of time. So unfortunately, this scenario does not hold every time, and this is quite obvious that in realistic applications, practically every realistic application, we do not have access to the transition structure between states. So for example, if we are trying to drive some autonomous vehicle and we want to either accelerate or decelerate in order to, I don't know, for example, avoid some obstacle due to other vehicles nearby creating them. So we can predict to some extent what the state will be after we make the action. But because the environment is stochastic and we do not have control over other actors in this environment, we cannot know exactly which state we will get to. And because of this stochasticity and because of this inability to predict the next state exactly, we cannot apply the value iteration and policy iteration algorithm from the previous week and homework. So we need to do something about it. And starting from this week, we'll start to cover the methods which can work in unknown environments with unknown rules, and where the agent should figure out how to find the optimal action, find the transition table of the environment by itself, just by playing, interacting with the environment and collecting information from the past episodes. So let's firstly start with warm-up test, and let's discuss the questions. So first of all, state value function, or in other words, V function. So what does this function actually describe? What does this function represent? So V function has two arguments. The first argument is the state. So V function takes as an input state of the process. And the second argument is not given explicitly. Well, basically, it's an implicit argument which is given as V pi index. So value function is defined for any policy that is compatible with this environment. And this function tells us how good this policy is. So how can we measure how good the policy is? And this measure is the expected total reward for the agent if the agent is governed by policy pi. So the agent always selects actions based on this distribution, this probability distribution pi. And the output of the value function will be the expected total reward with discount if the agent starts from the state S and acts according to the policy pi. So the first answer is correct here. Well, there is the dual function to the value function, which is called Q function. And we'll work with Q function mostly for today and next week, I guess. So Q function is basically the same as the value function, but it basically differs from the value function in the argument set. So Q function takes two arguments, state and action, and it outputs the expected total reward with discount if the agent starts in the state S, commits to making action A firstly, and then acts according to the policy pipe. So the difference between those functions is this action that for the Q function agent is obliged to make, and for the value function agent does not. So Q function tells the expected total reward if the agent selects action A in state S, and then continues to act according to the policy pipe. So those were introduced last week, so I hope that's not any news for you. Then let's move to more relevant to the model 3 setup questions. So first, let's try to understand what is model 3. So what does model in model 3 learning means? And here, model is essentially the inner structure of the environment. So a set of rules how the environment works and what we will get after the action that we commit in this environment. So here, most of you got this right. So model is the environment model, which tells us what will happen next and with what probability. So the final question is for Monte Carlo, is connected to Monte Carlo sampling. So first, I'll give a short answer so that we don't need to return to this form later, and then we'll discuss it in more detail. So Monte Carlo sampling basically is a tool according to which we can estimate the returns, the value function, and the transition model of the environment without knowing the exact mechanics. So Monte Carlo sampling is basically a form of sampling which we make from our past experiences. So Monte Carlo sampling requires full episodes to make an update. We'll cover why. And it's guaranteed to converge for a given policy if we explore sufficiently. So the second option here is also correct. And it cannot learn on partial trajectories because the variant which learns from partial trajectories, the one that most of the lecture was designated to, is called temporal difference. So we'll look into the difference more precisely in a couple of minutes.
Nikolai, can you say again? So the second question, guarantees to converge, is also correct, right?
Yeah. So it's guaranteed to converge for a given policy if the policy visits all states with high enough frequency.
Okay.
So I think the answer
it was not written quite well, yeah, and it's hard to guess that it can guarantee.
Yeah. Okay, so let's discuss what's going on in model 3 learning in more detail now. So I'll share a screen with the message board. So hopefully it's possible to see now. So yeah. So can you see the board or?
Yes.
Yeah.
So it guarantees convergence probably at the limit of infinite number of steps, right? Okay.
Yeah, sure. So let's first start with the previous value iteration algorithm. And in value iteration, we could recompute value of the state with the expectation. So first we have this expectation, which is essentially a sum of the next states that we can get to. So we sum probabilities over well, let's start with Q function, not V functions. I think it will be easier to understand. So in value iteration, or in this case, Q value iteration, we can recompute the Q function for a given state and a given action with the estimate of the Q function and value functions for the next state. So we first have this expectation over the next possible states. So those are probabilities of the agent getting into the state S prime if the agent makes action A from the state S. So this is exactly the world dynamics here. And what we average with these probabilities is the one-step reward from state S, action A and state S prime, plus discount factor multiplied by value function of the next state. So this is the recurrent formula from the week before, which we optimized. Well, not a good word, optimized, well, which we used to get the best policy with dynamic programming. So here, remember, we had a horizon of finite number of steps, and for each recurrent update, we extended the horizon for one step further, and in the limit, the horizon has become infinity. And infinite horizon meant that we eventually stabilize and have the exact solution for our MTP. So let's rewrite this with Q function. So with Q function, we have the same sum over the next state S prime, probability of S prime, given S and A. And then we have the recurrent estimation of the total discounted reward for this episode. So here we can substitute the value function with maximum function over possible actions. S prime and let's say action prime. We take here the maximum. Yeah, so why can we substitute V function with Q function? Well, because what is our best policy in the greedy fashion? So if we know values of each action in the state S prime, which action will we commit? The logical solution here is to commit action A prime. So this is a value iteration, and the ingredient that is missing in the most real-life scenarios is this transition model. So this is missing, and we need to do something about it. So the main question is, where from do we get this probability distribution over the next possible states? And how can we plug our past episodes of game playing or interacting with some environment, not necessarily game playing? How can we plug the past episodes to estimate these probabilities? So any suggestions?
Sample many different steps and count how many times we moved from S to S prime with action A.
Yeah, so this is the first very logical solution. So we can sample a lot of trajectories from our policy and estimate these probabilities by sampling from these trajectories. So here we can have those trajectories S let's say we make action A, and we get to S prime. We make action A prime, and we get to state S2 primes. So the problem here is that, let's say we are training an autonomous vehicle. Well, not a very realistic example, but let's say we're training an autonomous vehicle in discrete world. So states are discrete, and there is high enough probability that we get to the state S more than once. So let's imagine that we're training an autonomous vehicle in two-dimensional game where each state is represented by a position on the map and the velocity. So in this case, the environment is discrete. So the problem is that once we have moved from state S to state S prime, in most realistic scenarios, we cannot return to state S. And because of that, it's hard to compute these probabilities exactly. Yeah, so we cannot. So in order to compute these probabilities exactly, we first need to play very many episodes and track all the possible states we can visit from state S. So we need to first finish the first episode. Well, we move somewhere and somewhere else, and it can go on for a very long time. Then we need to play some more episodes or a number of episodes and track the number of times we reached state S in those episodes. So this requires a very large amount of game playing, of logging, and is very impractical. So what we can do instead of this is we can use sampling. So we can use sampling with moving average, to be more precise. So there are two variants of sampling. So first variant of sampling, as you have said, requires to sample, let's say it will be, there is no such notion in literature, so let's call it, but for simplicity, let's call it static sampling. So static sampling is exactly what we discussed now. We need to sample some trajectories and estimate probabilities directly. Directly, I mean that we estimate probabilities in numbers and then plug it as probabilities in this formula. So it's impractical because we need to play a lot of sessions. So what if we can make an update? What if we want to make an update for each trajectory? So what if we could make an update here? So how can we do this? And this can actually be done with the moving average variant of sampling. So in moving average averaging, basically we can substitute the honest averaging with rolling averaging, where we, for example, let's say we have Q function n, which is the honest averaging of the sum of Qi. So not to confuse you, this Q function is not related to this Q function. It's just, for example, of moving average. So how can we recompute, how can we rewrite this formula so that we can deduce average of n samples with the help of average of n-1 samples and the next sample. So we can rewrite this as follows. It will be 1 over n, sum of I from 1 to n minus 1, qi, plus qn. So nothing difficult going on here yet. And this can be represented as 1 over n average of n minus 1 samples multiplied by n minus 1 plus the nth sample. And this in turn can be represented as our previous moving average for n minus 1 samples plus the nth value that we want to average it with the previous estimate. So here we get n minus 1 over n times our previous moving average plus 1 over n qn. Yeah, so is it clear how we got this formula for average of n samples using the average of n minus 1 samples and the final sample? So is this formula clear here?
Yeah, clear.
Yeah, great. So how can this help us with the Q value iteration? So this can help us with the Q value iteration in the way that we don't need to estimate these probabilities directly. We can sample these trajectories and recursively and iteratively update this expectation averaging as long as new samples occur. So let's say it in other words. So first we play some number of sessions, and let's say we first visited state S, and this is the first time that we have made action A. So now we have one sample estimate from this distribution. So sample of size 1. So this is not a very good estimate because, well, sample of size 1, it can be very noisy. But we can compute our Q function for state S and action A because, well, we have a noisy estimate of this Q function for state S and action A, but it is better than no estimate. So we can compute this estimate from one sample. Now we have played a couple of more sessions, and it occurred that we have visited state S and made action A for another time. So now we have our previous estimate from the first time that we have visited state S and made action A, and we can use this previous estimate and add our new value from the trajectory because we have this moving average property of averaging. So let's write it as follows. So we have visited state S and made action A, and we want to recompute our estimate of Q function based on our previous estimate of Q function and the value from this trajectory. So let's say we have this thing here as beta. This will be 1 minus beta. So this beta is typically called the learning rate of the Q-learning algorithm, and basically is hyperparameter, so we can in practice use our own learning rate values. So from this formula over here, let's rewrite how we update Q function when we have visited state S and made action A again, and we have our previous estimate of Q function from our past experiences. So first we have beta times Q alt of S and A plus 1 minus beta. And here we have the new sample from the distribution. And what shall we sample here? So we sample values because Q function is the averaging of the value of each trajectory here in brackets. So the value here will be reward, one step reward, plus gamma multiplied by the maximum over actions, Q function for the next state. And this algorithm is called Q-learning. So this is the algorithm that we'll implement in this practice session. And basically, it iteratively updates Q function for states and actions that it visits. And for this goal, it uses moving average for sampling from probability distribution of state S prime, given state S and action A. So basically, this is the main formula for today's practice session. In other words, Q-learning does not differ very much from Bell iteration. The only difference is that we substitute these probabilities in the expectation with the estimates of those probabilities, which we compute indirectly by sampling from our policy trajectories and averaging them with the moving average in the moving average fashion. So I think that here can be many questions on how this works and why does it work. If you have any questions, I'll be glad to answer them. If not, we'll move to implementing this algorithm in practice, and hopefully we'll see how this works in more detail. So if you have any questions, feel free to ask. Yeah. Okay. Let's look at the implementation. So as always, you can go to the repository, and in the repository, visit week number 3. And here you'll see the practice notebook and the homework for the next week, for the next 1.5 weeks, to be precise. So let's open the practice notebook. So today we'll train the Q-learning agent and see how this Q-learning algorithm will work in the environment of taxi v3 from Atari. And then we'll try to binarize state spaces to apply Q-learning for infinite state spaces. So first, let's walk through the properties of this Q-learning agent, and let's see what it does. So first of all, we have a set of hyperparameters, alpha, epsilon, discount. And what do these hyperparameters describe? So first we have this epsilon here. Epsilon is the probability of exploration. So we'll cover it when we get to the exploration part of the code. Then we have this discount. Discount is already known to us. It's the discount rate of the process, the gamma multiplier, that we multiply the further returns to penalize long-range returns over time. So we want to focus on the returns that we would get soon over the returns that we will get later on after 1,000,000 steps. And this alpha multiplier is the learning rate from the Q-learning algorithm, and this is basically the speed at which we mix the moving average from the previous step and the sample from this step. So the larger this alpha here is, the faster the more aggressive we involve the new sample from the distribution into our moving average over n steps. So typically, alpha should not be too high to make the averaging more stable. So also we have the function which returns legal actions for a given state. So for any state in the decision process, there are predefined set of actions that we can commit in the state. So for example, in chess, if we are under if we are in the start of our board, there are some actions that we cannot commit, and those are governed by the set of actions that we can make for a given MDP. So MDP tells us which actions we can make and which actions we cannot make from the state. So what this Q-learning algorithm stores under the hood? So basically, we have a large dictionary of the state, and for each state in this dictionary, we have a dictionary of actions. So we can query this dictionary of Q-values with two arguments, state and action. And as a result, we get our current estimate of Q-value for a state and action. So this is the expected total reward with discount if we act according to our policy pi and start with the state and make an action. So here are a couple of methods which are used to set these Q values and get these Q values. Typical interface. Nothing connected to the reinforcement learning yet. So first, let's start with how we compute our agent's estimate of value function. So remember, we had this recurrent formula in which, so let's see this formula first. So we had this recurrent formula with the help of which we could recompute the estimate of Q value for state and action for a given state and action under the policy of our agent. So here we have this value that we get from our trajectory. So our trajectory is what states, actions, and rewards we got in the current episode. And we mix those current states, actions, and rewards knowledge from the current episode with the previous estimate of our Q function from the previous game playing, from the previous interaction. So here we have this value, and the value for this trajectory for state S and action A is basically how much we got, how much reward did we get in this trajectory after we have made action A in state S. So this total reward will be composed of two values. So first we have one-step return. So one-step return is basically the reward that we have got immediately after the step A in action, we have made action A in state S. So this is our one-step reward. To get total reward for our episode, we have kind of hack here. Instead of rolling the episode until the end and computing honest reward for each step, we do not wait until the end of the episode, and we basically, instead of taking the honest total reward from the state S prime, we query our current estimate of how much we get reward from state S prime onwards using our Q functions. So here we have Q function over state for state S prime and arbitrary action A prime. And to get the value of state S prime, we can simply compute the maximum of Q function for state S prime action A prime over all possible actions. So this will be exactly equal to the value function for state S prime from our previous algorithm value iteration. So how can we compute this value function for the state using current Q values? So first we get all possible actions for the state. If there are no possible actions, we return 0. So if there are no possible actions in the state, there is simply no way that we can get any positive reward if we start with this state. If there are possible states, we simply look into our Q values and pick an action which returns the most value according to our current estimate. So value will be equal to maximum Q values for state and action for action in possible actions. So this is a value function for state equal to maximum Q function for state. In other words, we always try to select the best action according to our estimate how much this action will give us at the end of the episode if we follow our current policy. So that's how we compute our value function for a state. So now let's move to Q value update here. So what does Q value update look like? So first we have our previous Q function estimate. So this is our previous Q function estimate that we store in our dictionary, and we use this estimate in order to mix our previous estimate with the current value that we have got from our current trajectory. So first we have Q value from trajectory. And this will be equal to our one-step reward plus self-discount multiplied by the value of next state. And new value will be basically got from an update with moving average when we average our previous Q value and the Q value that we get from our trajectory. Here we can write gamma. So our new Q value will be equal to 1 minus learning rate multiplied by self-get Q value for the state and action plus learning rate multiplied by Q value from the current trajectory. So that's how the update looks like. So let's look again what's going on here. So we want to improve our estimate of Q value for state and action. Last week, we could exactly compute the mathematical expectation over all the possible next states in our environment when we averaged the probabilities of those next states. Yeah, so last week we could compute this thing here. Today, we have no access to those probabilities of the next states that we get to when we commit action A in state S. So now we need to substitute those probabilities with sampling. And unfortunately, we cannot sample all the trajectories beforehand and estimate probabilities from those sampled trajectories. We need to do this on the run. And to do this on the run, we use moving average technique. So in moving average, we get away from this static averaging with these probabilities. And we simply sample as many trajectories as we can. And after we have sampled our next trajectory, we mix the value that we get from the sampled trajectories in these square brackets with the previous moving average estimate of Q function. So the formula over here. And the final update will look like this. So here we have, first of all, the moving average from the previous step, which we store in the dictionary of our Q-learning agent. And we mix the previous estimate of Q function with the value that we have achieved from sampling from the current trajectory. And the value that we achieve from the current trajectory is basically one step reward plus gamma multiplied by the value function of the next state. So that's it. That's how Q-learning works. So this way of estimating value for a trajectory is called temporal difference. So this is called temporal difference. And this is kind of approximation because we make an update at this time step. So update will come here. And if you look carefully, you'll see that this update is not exactly honest. Because if we try to be very precise and have a mathematically correct update, we need to compute the total rewards until the end of the episode. So let's imagine that here we'll have the terminal state. To get an honest value for total reward for this trajectory, we need to roll this trajectory until the end and sum one-step returns for each step. So we'll have R, R1, R2, and so on and so forth. So this will be the honest total reward for the episode. And this is called Monte Carlo sampling. So in Monte Carlo sampling, we need full episodes to make an update for our Q function. And this is not very great because, first of all, we need to wait very long until an update. And secondly, for infinite step environments, for example, like self-driving cars or some robotic arms which do some assembling or disassembling of goods, we do not have end of the episode. And we need to make an update quicker. So to make an update quicker, we use our previous estimate of this total reward for the state S prime instead of exactly computing it for the current trajectory. So we substitute our samples with the estimation of the sample for the next state S prime. So that's how temporal difference works. So if you have any questions, I think now is a good time to ask them.
For temporal difference, do we also have guaranteed convergence?
Yeah, for temporal difference, we also have guaranteed convergence. I'll not dive into mathematical explanation why this is so, but the convergence guarantee also holds in this case. Also, if the agent sufficiently explores the environment, so if it visits enough states and actions for a definite amount of times. So, for example, if the agent does not visit any state at all, so for example, if the agent tries to, if the agent is some robot which is trying to learn how to walk. So, for example, let's say the agent has sampled action fall, simply fall slightly towards the goal. So it will move slightly toward the goal if the agent simply falls and not makes a step with its legs. So it's closer to the goal than it was before. And if we have a reward which gives us more points the closer we get to the goal, we will get a slight positive feedback. So the agent has fallen, it has fallen towards the goal, and it has moved closer to it. And if we do not explore our environment and always pick the best possible action, then the agent will not find out, will never find out that there are other good actions that it can commit to move forward. And that's not very good. So all these algorithms, all these value-based algorithms work well only in the case when we explore sufficiently the environment. Can you re-explain how to use Monte Carlo sampling and compute it? Concretely, what changes in the formula? Yeah, sure. So I think I can erase most of the notation here. I think we do not need moving average explanation. So in Monte Carlo sampling, the difference is that we use honest total discounted rewards for the episode. So temporal difference, once again, over here. So in temporal difference, we make action A and get to state S prime, we get reward, and we don't care what happens next. So in temporal difference, we fetch the Q value for the state S prime, and we say, well, we do not want to roll out the episode until the end. We know that our estimate is good enough, and we substitute the total return from the state S prime onwards until the end with our current estimate. And in Monte Carlo sampling, we roll our episode until the end. So here we'll have action 2, reward 2, some new state, and so on and so forth, and some terminal state. And in Monte Carlo sampling, we simply have moving average, Q of SA equals to beta times Q alt of SA. So that's our previous estimate of the Q function. And we add the total reward with discount from this episode. This will be one step reward plus gamma reward 2 plus gamma squared reward 3, and so on until we get our final one-step reward and terminate our episode. So we have gamma to the power of n reward n plus 1. So you can see here that this is an honest moving average of total reward with discount, which we get from state S and action A. So this is the same as this is basically the same as the honest averaging from sampling. One over n multiplied by RSA 1 plus RSA n. So in other words, Monte Carlo estimation is simply a moving average, averaging of all rewards with discount for all episodes in which we have visited state S and made action A. So this is kind of an honest averaging for all the episodes that we have been in this state and this action. So here these are capitalized is total return with discount for the whole episode. And so this is Monte Carlo. And this is very long to compute because we need to have the full episode until the terminal state to make one single update for this state in action. And we do not want to wait this long for an update. We want to update immediately after we have made the state S, action A, and got some reward. So this is there is some signal here that we want to exploit. And in temporal difference, we have an approximation to the first formula here, to the Monte Carlo. So we, in the same way, have a moving average, where we average our previous estimate for Q function with what we get from this trajectory. And the difference is how we estimate the total reward with discount, which we get from this trajectory. So here we had this gigantic sum of one-step returns. And here we substitute this gigantic sum with only one step reward for the first step, for this step. plus gamma multiplied by the value function of the state S prime. So this value function is the estimate of this quantity here. And this value function in turn is equal to the maximum over all possible actions that we can make in the next state, Q function for the next state, and possible action in the next state. So that's temporal difference. So any other questions? So let's return to the implementation. So this is the update that we have seen just now in the mathematical notation. That's how it looks in the code. So how can we, so now let's move from the estimation to the inference. So inference means we want to program the agent to pick action in a given state with the help of our Q values. So we have our Q values, they tell whatever, how good some action is in some state, and we want simply to perform best according to those Q values. So here the choice is very clear, I hope. We want to pick the best action according to our estimation of how good these actions are. And our estimations of how good these actions are is stored in Q values. So we want to pick the best action to take in a state. Best action will be equal to let's store Q values for legal actions in dictionary. So in this dictionary, we have stored now Q values for all possible actions in the state S. And we want to pick the argmax of Q values to choose the best action.
Is it max or argmax?
Well, it's argmax, but there is no such function in Python, so we take max over dictionary
NumPy,
with this key.
We can use NumPy argmax.
Well, yeah, we can. But let's stick with the library functions for simplicity. I don't know if it's if it looks simple or on the other hand confusing, but nevertheless, we query the Python dictionary with this key. So we pick the best key. We pick the key with the greatest value. So now we know which our best function, which our best action is. But it's good to always select the best action for an agent according to our current estimate. So our current estimate is imperfect, especially at the beginning of our training. And we do not want to always select our best action in a greedy fashion. So if we do so, we'll get a behavior as in the example with the robot which learns to walk. And the robot learned to crawl, and the robot sees that crawling is better than standing still with no action. And crawling basically moves the robot closer to the goal. So it's better than nothing. And if we select actions in a greedy fashion, the robot will not learn anything else. So the robot will not learn how to walk, and the robot will not learn how to run. And if we want to train a robot with a good quality, well, we possibly want the robot to see these actions. So we possibly want the robot to see the outcome of this action to learn from this trial and error. So that's why sometimes we want the robot to pick not optimal action in order to see other actions and probably get some knowledge that it doesn't have for now. So this is called exploration, and this is one of the fundamental problems in reinforcement learning. So in reinforcement learning, we need to explore the environment sufficiently to extend our knowledge of its mechanics and what is good and what is bad. And at the same time, we do not want to do some rubbish. We want to do some sensible things most often. So this is called exploration-exploitation trade-off. So we want to explore, and at the same time, we do not want to explore too much, because if we explore too much, well, we will do some random stuff and we'll not get any reward if we do so. So in this Q-learning agent, we will implement one simple exploration strategy, which says the epsilon, we take a random action. So epsilon is some floating number which is not too high. So let's say it will be 1% for simplicity for this explanation sake. And with 1% probability, we take a random action. And with 99% probability, we take the action that is best according to our knowledge. And if we take the example of robot which learns how to move, and the robot has learned how to crawl, we will be continuing to take random action with some probability, 1%, and we hope that sometime in the future, the robot will select a good action, a very good action, and find out that this action is better than the current optimum. So we have this epsilon hyperparameter. And we sample a number, and with probability 1 minus epsilon, we select best action. And with probability of epsilon, we choose an arbitrary action. So that's how our agent will behave. So let's quickly walk through the implementation once again to get it together. So first we have the dictionary of Q-values, which store our current estimates of Q-values, how much reward we will get for following our current policy from state S and taking action A first. Then once we have Q-values, we can compute values for a state, and a value for a state is the maximum of Q-values over all possible actions. So we get Q-value for each possible action in the state, and we simply output the maximum. Then we have this Q-values update, and Q-values update is the moving average update using our Q value from the trajectory, computed using temporal difference. So temporal difference reward plus gamma multiplied by the value of next state. And we mix the Q value from trajectory with the previous estimate of Q value from all the previous trajectories, from n-1 previous trajectories. And we mix those old Q value and Q value from trajectory using the moving average and learning rate, which is the hyperparameter. So new Q value will be equal to 1 minus learning rate times the previous estimate plus learning rate times the Q value from trajectory. So how do we compute the best action? The best action is simply the action with the highest Q value for all possible actions in this state.
What does it mean, key equal to Q values for action get?
So let's have an example. We have a dictionary, Python dictionary. So
With brackets.
Yeah. So each dictionary in Python has a function get, which takes as an input keys. And the function get returns the value for this key. So here we compute the maximum of all the keys in this dictionary Q values for actions. And key to compute our maximum will be this function. So in maximum function in Python, in built-in function maximum, we have this argument key, and key can be function itself. So we select the maximum from this iterable with using this function for comparing these elements of the iterable. So this will give us the argmax of the dictionary. So if we have this maximum of A equal A get, we will get C because it's equal to 3.5.
Okay.
So now we know how to compute the best action. So let's use some exploration, and with probability of epsilon, pick some random action. And with probability of 1 minus epsilon, let's pick the best action according to our estimate. So that's how our agent will work. So let's train it. How do we train our agent? So we play and train simultaneously. So we reset our environment, and at each time step, we first pick action according to our strategy, to our policy. So agent is equal to, so A action is equal to agent get action for the state S. So now we have selected our action. It can be the best action according to the Q values, and it can be a random action for exploration. So now we have selected the action and we make a step. We made a step, we have got our partial trajectory, and we update our agent using the temporal difference formula, basically. So we call agent update state as action A, reward R. Next state is the state that we see from this sample. So that's all. So let's see how good it works. So here is a plot which changes over time. And this plot shows us the mean reward of our agent in the game taxi. So you can see that it started with the minus 600 points, which corresponds to completely random strategy. The agent did something arbitrary. And then it quickly converged to mean reward of 7 points. So that's pretty good for this environment. So one important thing to notice here is that we gradually change our epsilon. So why should we do this? So epsilon is the parameter which controls us how aggressively we explore our environment. So question for you, what do you think is better, to explore more at the early stage or to explore more at the late stage?
At the early stage.
So why is it better at the early stage?
It should converge sometimes, so we need to explore less and less at the end of the day.
Yeah, that's correct. So we want to explore more at the early stage because if we do everything correctly, after some time, our agent will become good enough and will know a lot about the properties of the world it is located in, and hence we do not need to explore very much at the later stage. And at the initial state of the agent, when it does not know anything, it would be a good idea to explore very aggressively because, well, our estimate will likely be very incorrect. So that's how Q-learning works. So you can see that it works pretty well for discrete state spaces, and it converges pretty quickly. So this is a good and solid algorithm to use for tabular spaces. Tabular means
go back one step back. The last procedure. Yes, a bit.
Yeah. So
I see. You did update here. Mm-hmm.
Yeah. So our Q-learning algorithm works pretty nice in tabular cases. Tabular means we can enumerate all states. So number of states is finite and not too great. But what if we do not have finite number of spaces? So for example, let's look at card pool environment. So card pool is a game in which the player needs to balance this stick here so that it does not fall off the table. So we can control these, I don't know how to call it. We have control over this stick and we can move it either to the left or to the right. And depending on where we have moved the stick, the object, the card, will move either to the left or to the right. So there is some inertia going on here. So if we move the cards to the left, if we move the stick to the left, the card will start accelerating to the left, and so on. So the goal here is to balance the card for as much time as possible on this table without going over the limits on the horizontal axis. So card can go over the canvas border, and this will be a lost episode. So we need to balance it for as much time as we can. So in this game, we have a continuous number of states. So the state will be card position, card velocity, pole angle, and pole velocity at tip. So 4 numbers. Each of them is a floating point number. So in this scenario, we cannot apply Q-learning algorithm directly because we cannot have a gigantic table which will memorize all the possible states because the number of states is infinite. So we need to do something about it. So, and one way to use these tabular algorithms for continuous states is to use binarization technique. So binarization is a technique to somehow make infinite state spaces finite. So how can we do this? In this case, we can simply round the coordinates to some precision. So for example, we can round these coordinates to 2 decimal points after to 2 decimal points. And this will give us much less possible states, and we will be able to memorize q-values in the table then. So let's look at how it works. So first we have, let's see, a histogram of observations that we have. So we have card position, and you can see that possible positions of the card in this game are somewhat close to 0. So they are not too high. They're quite low, actually. And if we round the observation to 2 digits after decimal point, we will get not too many possible states. So we will get 50 states here and 50 states here that are possible to achieve in the binarized case. Sorry. And if we look at the velocity, we will see that we can binarize not too precisely here. So we can probably round to 1 point after to 1 digit after decimal point here, and get a reasonable and finite number of states. And the same with pole angle and pole velocity. So let's try to binarize. So let's have this binarizer wrapper, and as the input to this function, we have the state. And we can modify the state, and the agent will see the modified version of the state. So we have as input the continuous variant of the state, and as output, we want to have a finite representation of the state. So we round the floating number into an integer, or not exactly integer. We can round to floating number with less precision, and we will have much less states in the end. For example, let's round first part of the state to 2 decimal points. Let's round this second part of the state to 1 point, third also to 1 point, and the fourth also to 1 point. And see how our algorithm will work in this case. So let's also create a learning agent. Let's adjust epsilon here. So it's always a good thing to try to adjust exploration rate, epsilon parameter here, for your own purposes. So you can make it static, you can make it change over time, and the exact behavior is probably different for any case that you're pursuing. So for our training, let's decrease epsilon with some exponential factor for each step. Agent epsilon. So you can see that the agent has started to train with, I would say, reasonable efficiency. So good performance in this environment will be a reward of around 50. And we are getting there. So we have achieved this pretty good performance with tabular q-learning for the continuous state space. So how did we do this? We binarized the environment, and you can see that in binarized environment, we have only 5 possible states for pole angle, and this is sufficient. So we binarize the environment and we make the reachable set of states not too big. And this will allow the tabular Q-learning to train in the continuous case. So that's how this trick works. So I guess that was the core idea of the Q-learning algorithm that we've covered so far. And this week we have another homework. I think this homework will be for 1.5 weeks. And in this homework, you'll use the same Q-learning implementation, and also you look at the expected value SARSA algorithm, which differs from the Q-learning algorithm in the strategy how we compute the v-pi for a state. So the task will be to train an expected value SARSA agent and compare it to Q-learning agents in the Clifford environment. So this will be the first task. And the second task will be to implement the experience replay buffer to improve sample efficiency. So the goal of experience replay is to store the past interactions in the replay buffer, and it will mitigate the issue of non-stationary process, which I think Radoslav has covered in the lecture. So here is the class of replay buffer, and the goal is to train an agent with replay buffer and sample trajectories not only from experience, but at the same time from the buffer. So it should converge quicker than the vanilla implementation without replay buffer. So that's the homework. That will be the homework. So also one organizational notice, in the next couple of days, we will launch the course page on Stepic, and this will be the way to basically the main way to send in the homeworks, to get homework deadlines, to get marks. So it will make the communication much easier. So that's the reason why for the first homework we did not have a link for submission. We are waiting for the Stepic page to launch. So we are waiting yet. I hope it will launch tomorrow or so. Will we upload first homework there? Yeah, so I think that once we set up the Stepic page, there'll be a possibility to upload first homework there, and also we'll extend the deadline so that you can upload the homework into Stepic and get it for those of you who had problems with finishing it by today because of the confusion with the submission system. It will be possible to submit, I think, tomorrow or the day after tomorrow also. So I'll put the detailed information in the chat. Yeah, for those of you who sent the homework to the Telegram address, it's also it will also be accepted. But I think for your own purposes, it will be more. It will be simpler to send it into the Stepic page when it's available, to get so to say, not to have some miscommunication with grading and submission of the homework. So any more questions on the organizational part or on the material, whatever? What is the deadline for the second homework? I think the deadline will be the weekend, not the closest. I think the deadline will be the end of the next week. So the duration of the homework will be a week and a half. So it's not very difficult. It's I would say it's slightly more there are slightly more coding in it than in the first homework. But if you look at the theoretical part, it's very simple because all the formulas are put in the notebook. So you only need to implement it in the in Python and train the agent. Yeah, Sunday 14th evening seems right.
It will be a week and a half for all homeworks or only for the nearest one?
I think I can be sure only for the nearest one. Also, for the rest of the homework, week and a half seems a good default choice. But I think there will be homeworks which are difficult enough to make them 2 weeks and a half or so. So if there are no more questions, then that's it for today. See you next week.
Thank you. Bye-bye.